Hello, my name is Michelle Bertram, and today I will be discussing the heat diffusion equation in 2D. The learning objectives today are to define what the heat equation physically means, how to solve this heat equation while applying boundary conditions and set a reasonable initial condition for the heat equation, and use our knowledge of mathematical meaning behind the heat equation to apply it to coding and create a spatial map of the heat equation. To understand the mechanism behind the heat equation, you must understand what it physically means. The main assumption made for this model is that we have a negligibly thin plate of conductive material. Heat is allowed to flow through the material. The purpose of the heat equation is to mathematically model the flow of heat through this plate over time. We also make the assumption that the plate is under an ideal condition, such as uniform density, uniform specific heat, perfect insulation, and no internal heat sources. Finally, we impose boundary conditions such that there is no heat flux through the top and bottom of the plate, indicating perfect insulation, while there is heat flux in the x directions. In the case of no heat flux, we will be applying the Dirichlet boundary conditions, while heat flux allows for the Newman conditions. We first start with the basic form of the heat equation. This is where diffusivity is different in the x and y directions. We then constrain x between 0 and the total length of the rectangle, notated as L. We do similarly with y, constraining it between 0 and the height of the rectangle, notated as H. Then apply the given boundary conditions, constraining the boundary of x to the Dirichlet conditions, which allow for heat flux, then constraining the value of y to the Newman boundary conditions, which indicate perfect insulation. An initial condition is then applied. In this case, we assume that t equals 0, making the initial condition a function of x and y, or just position only. To begin calculations, we make the assumption that our equation could take the form of capital X as a function of lowercase x, multiplied by y as a function of lowercase y, as well as t as a function of lowercase t. Utilizing the assumption and our initial conditions, the partial differential equation takes on the form where x, y, and t are all in the equation, and k1 and k2 are the constants that were in the initial 2D heat equation. Since this is our equation, for the form for the 2D heat equation, we will use this in further calculations. The equation can then be rearranged as so. Since the left-hand side depends on time and the right-hand side is a function of position, both sides must be equal to some constant. In this case, we will call this constant negative lambda, because this will be our separation constant. Take only the left-hand side, the temperature condition of the equation, into consideration. The equation can be rearranged to solve for capital T as a function of time, as so. We then take into account our Dirichlet and Newman boundary conditions. After solving for T, we begin to solve the right hand of the equation for position. The equation can be rearranged like so. Since both the left-hand side and the right-hand side are equal to a constant, we will assume them equal to mu. Taking into consideration only the x part of the equation, you could rearrange the condition like so. We then apply the boundary condition in the x direction. Using the positive eigenvalues, two different solutions are determined. Similarly, the y side of the equation is also rearranged. We then solve using the positive eigenvalues of y to get the PDE in this form. Note how y takes on the form of cosine, while x takes on the form of sine. Rearranging the solutions for both x and y yields this answer in terms of lambda, which can then be rearranged and solved with our initial form of the heat equation. Now that the heat equation has been solved, we can apply this knowledge to coding. There are some logical steps that must be taken to code the 2D heat equation. You must input initial parameters, which include diffusivity, grid points, grid spacing, number of phases, time steps, A, sigma, number of loops, and your left and right boundary conditions. You then allocate the memory over x, y, and the number of phases, the three variables that we use to solve for in the 2D heat equation. You then deallocate the memory in order to save on processing power and RAM. You must then code to solve for the phase field equation for 2D heat. This requires inputting the solution that we previously solved for analytically. You then apply the Dirichlet and the Newman boundary conditions, as we did when we determined the analytical solutions. You can then output the data as a file, which can be plotted using open source software such as GNU Plot, which is what was used here. From a positional profile, the data will look like the graph on the top, while incorporating both time and position will yield the 3D compositional gradient on the bottom. Thank you.